Hi there, I'm Amano. Welcome to the channel, where we talk about math in a relaxed, easygoing way. So just sit back, take it easy, and enjoy listening. Today's topic is the formula for the volume of a sphere. As you probably already know, the volume of a sphere is 4/3 times pi times r cubed. And every now and then, someone asks me this question: why does that fraction, 4/3, show up in the formula? That's exactly what we're going to talk about today. All right, let's get started. Section 1. There are several ways to explain the formula for the volume of a sphere. First, let's go with the most mathematically clear explanation. We're going to use integration. Now take a look at this diagram. Imagine a sphere with radius r. Let's set up the x-axis and y-axis so they pass through the center. Pick a point P on the surface of the sphere. Through that point P, slice the sphere cleanly with a plane that is perpendicular to the x-axis. The cross-section you get is a circle, this red region right here. Let the coordinates of point P be x, y, and the radius of the sphere be r. Then a right triangle appears. When you see a right triangle, what comes to mind? Of course, the Pythagorean theorem. X squared plus y squared equals r squared. We can rewrite this as y squared equals r squared minus x squared. Keep this equation in mind. We'll use it in a moment. Next, let's call the cross-sectional area of the sphere A of x. This area changes depending on the value of x. Since the cross-section is a circle, using x we can write A of x equals pi y squared. And using the earlier equation, we can rewrite it as A of x equals pi times r squared minus x squared. To get the volume of the sphere, we add up infinitely thin circular disks from the left end to the right end. As you know, that's exactly the idea of a definite integral. Here's the equation we need. V equals the integral from minus r to r of pi times r squared minus x squared dx. That finishes the setup. The rest is straightforward. We just evaluate the integral. When we integrate, we get r squared x minus 1/3 x cubed. Now substitute r for x and subtract the result of substituting negative r. We obtain r cubed minus 1/3 r cubed minus negative r cubed plus 1/3 r cubed. Simplifying, we get 2/3 r cubed minus negative 2/3 r cubed. Simplify once more and we get v equals 4/3 pi r cubed. And we're done. That's the formula for the volume of a sphere. The 4/3 shows up clearly and proudly right here. Using integration, we can explain the formula very precisely. Did this explanation make sense to you? For people who don't know integration, another type of explanation is often used. Section 2. This explanation is a bit more intuitive. The basic idea is actually the same as before. Look at this diagram. Draw a very tiny circle on the surface of the sphere, so tiny that you can barely see it. That red spot right there. Using that tiny circle as a base, cut out a solid whose tip is at the center of the sphere. If we think in the limit, this solid can be regarded as a cone whose height equals the radius. This way of thinking is essentially the same as integration. From here on, it's just simple calculations. Let the volume of this cone be V1, its base area be S1, and its height be r. Then its volume is V1 equals 1/3 S1 R. We repeat the same thing over and over. Call the volumes of the cones V2, V3, V4, and so on. Now imagine cutting up the entire sphere this way. Then the volume of the sphere becomes V equals 1/3 S1 R plus 1/3 S2 R plus 1/3 S3 R, and so on. Factor out 1/3 R. V equals 1/3 R times S1 plus S2 plus S3 plus, and so on. That's the first half. Are you still with me? You're doing great. The second half is simple. Focus on what's inside the parentheses. S1 plus S2 plus S3 plus, and so on. Do you know what this represents? That's right, the surface area of the sphere, because we're adding up all the cone bases. The surface area of a sphere is 4 pi r squared. Substitute this in and we get V equals 4/3 pi r cubed. Did you follow that? Strictly speaking, we should also explain why the surface area formula is 4 pi r squared, but that part is often skipped. This explanation works well for people who haven't learned integration yet. Summary. And that wraps up today's talk. So, which explanation did you like better? If you were explaining this to a friend, which one would you choose? I'd love to hear what you think. By the way, there's one more famous explanation of the formula for the volume of a sphere. It uses something called Cavalieri's principle. Personally, I think this explanation is very clear and pretty interesting too. So let me give you a rough overview. Take a look at this diagram. Here we have a sphere and a cylindrical container that fits it perfectly. The radius of the sphere is r. The base of the cylinder is a circle with radius r, and the height of the cylinder is 2r. We're going to compare the volumes of these two shapes. The volume of a cylinder is calculated by multiplying the area of the base by the height, so the volume comes out to be 2 pi r cubed. According to Cavalieri's principle, the volume of the sphere is 2/3 of the volume of the cylinder, so we can calculate the volume like this. When you work it out, the volume is written as V equals 4/3 times pi r cubed. That's the explanation using Cavalieri's principle. To explain this method in full detail, we'd need some more complicated diagrams and equations, so I'll skip that part today. If you're interested, feel free to look it up on your own. By the way, Cavalieri was an Italian mathematician from the 17th century. Thanks for watching this video all the way to the end. Next time, we'll talk about the formula for the surface area of a sphere. If you enjoyed this video, please hit the like button and subscribe to the channel. See you next time. This was Amano.